Alright, so to wrap up our work for this week, to wrap up most of our work on springs, we are still on Jupiter, so I've already sort of clicked that from the drop-down menu over here. Remember that it'll start out on Earth, but you got to click on Jupiter. And I put this damping down to the none, so that there's no internal friction within this spring. The mass is still the default 100 grams, and I've taken this spring constant up to the 5th notch. It'll start you on the 3rd, but I've moved this up to that 5th notch where your spring constant is 7.84 newtons per meter. And the last thing that we're doing today is with that mass on this spring, and right now I have it paused, your goal is to, with that same initial displacement that you had in yesterday's work, so I'll drag this down to the 75 centimeter initial displacement that we had before. So with that where it is, your goal is to pause this simulation once the mass reaches this mass equilibrium, so this black line right here in the middle where the mass would hang without any initial displacement or without bouncing at all. Your goal is to pause it right when the center of mass of this object is over this black line, and I'll show my attempts at doing that in a second. But then once you have it paused there, to calculate your elastic potential energy, your gravitational potential energy, and then making a prediction as to what that kinetic energy and then eventually the velocity are. So I have this clicked onto slow so that it's a little easier for me to do that. If you run the simulation on normal, it moves at a really fast speed and it's hard to pause it at just the right moment. It's already hard as it is, even when it's on slow. But I'll click play so that it starts going. And I've clicked this period trace box so that we can see sort of this black line that traces how high up the mass goes, how far down it goes, and then our goal is to pause it right here when it crosses over that midpoint, that mass equilibrium. So let's see if I can get that. It'll probably take a couple tries. Oh, that was pretty good actually. Okay, and the reason that I'm saying that was pretty good is we have this black mass equilibrium line right at about where the mass equilibrium is, going right through that center of mass. So that looks actually pretty good to me, and you can also tell from this period trace we've got right where we started, like where they started counting this oscillation, getting basically right down to where it stopped here at that mass equilibrium again. Okay, so as a reminder to calculate your other types of energy, so we've got gravitational potential energy is still mass times gravity times height, just like you all did yesterday. Make sure you use the 24.8 meters per second squared as the acceleration due to gravity, since we're on Jupiter now. And so when you're calculating that, to get that height, again, you need to make sure that you have this meter stick lined up so that the bottom of it, or it's really the 100 centimeter mark, is on this height equals 0 line at the bottom of the simulation. And then we can really measure up right to this line. So like here, you can sort of see what that is. And you would calculate that way. And for our elastic potential energy, that's actually a little bit easier to calculate. You just want to make sure you're using the right value of K, which should be, for this 5-notch spring, 7.84 newtons per meter. And then for that displacement, you would measure this green vector, making sure that you have the top of the meter stick down, or on this natural length line. Now for our kinetic energy, I'm going to plug in some made-up numbers just as an example. So let's say in yesterday's work we found that our mechanical energy was 10 joules. And then today, let's say I calculated these new values. I'm going to put the values at this point that I've paused it at. So let's say that when I calculated our gravitational potential energy, I got 3.5 joules. And let's say that when I calculated this elastic potential energy, I found that it was 2.1 joules. And so the question is, what is the remaining kinetic energy that gets us to that same total conserved mechanical energy? And so that's sort of what the kinetic energy question is on today's work, is we need to figure out, okay, if we know from what we've done before that our equation for mechanical energy, like broadly is our gravitational potential plus kinetic plus our elastic potential energy. If we know what this is supposed to be, how can we get this missing piece? And this is really sort of an algebra problem at this point. We've just got to make sure that we plug everything in the right spot. So I'm plugging in our 10 joules for our mechanical energy in this equation. I'm going to plug in our 3.5 joules for the gravitational potential. We don't know what our kinetic is, so I'm just going to leave that as Ke. And then we've got our 2.1 joule elastic potential. And so if you want to simplify this, you can. You certainly don't have to, but I'm going to do that here. So 3.5 plus 2.1 is 5.6 plus whatever that kinetic energy is. And so at this point, we can really subtract 5.6 from each side so that goes away there. And we would get that our kinetic energy is, it looks like 4.4 joules. And so that's how, even though we don't know a mass and we don't know a velocity, or we do know a mass but we don't know velocity, that's how you can still solve for that kinetic energy. We did that back with our roller coasters, and you all did that earlier in the week as well. Now, the one new thing that we haven't done this week is going from that kinetic energy to a velocity. We did do that a while ago, but it's been a while since we practiced that. So I'm going to take a second to go over how to do that again. It's how to calculate what that velocity is at this point that I've paused the simulation at, and getting that from this kinetic energy that we just found. So we're going to go from the kinetic energy equation, which is 1/2 mv squared, and we know that our mass is 0.1 kilograms, so 100 grams is just the same as 0.1 kilograms, and now we know what our kinetic energy is. So I'm going to go ahead and start plugging in the stuff that we know at this point. 4.4 joules is equal to 1/2 times 0.1 kilograms times v squared. And I think it's easiest to combine our terms that we can at this point. So I'm going to multiply our 1/2 and 0.1, which I think should be 0.05 v squared. And then we're just about one step or two steps away. So we've got something being multiplied by v squared. So to get rid of that, let's divide both sides by 0.05. And let's see, what's 4.4 divided by 0.05? That looks like 88 is equal to v squared, now that these 0.05s have canceled out. But we don't want to solve for what v squared is. We want to know what v, the velocity, is. So to get rid of that squared, we've got to take the square root of each side. And so let's see what the square root of 88 is. It should be 9 point something. Yep. And so it looks like that velocity at this point is 9.38, or I can also just write 9.4 meters per second. That's totally fine to round to just a decimal point. So again, you're using your knowledge of what the mechanical energy was from your yesterday work, and then getting your kinetic energy that way, sort of backwards calculating it. And then you're going backwards one more step to use that kinetic energy to solve for this missing velocity. So that's one added step sort of from what you all did earlier.